So our first speaker will be Paul Hayne, and he will talk about the Lunar Flashlight.
Okay, is this thing on?
I can hear you.
Great. So I'm going to talk about the Lunar Flashlight mission, and I'm presenting this on behalf of our PI, Barbara Cohen, who couldn't make it, and the whole Lunar Flashlight team, some of whom are listed here. So this is a low-cost, high-risk, high-reward mission that was originally selected by the Advanced Exploration Systems program within NASA's Human Exploration Directorate. So the objective of the mission is to identify water ice at the surfaces within permanently shadowed craters. Next slide, please. So this is sort of preaching to the choir, but the thing I wanted to point out here, and this is kind of a summary graphic from a Keck Institute study from a few years ago, where we sat down and talked about lunar volatiles for a couple of weeks and what measurements needed to be made to really advance the field. And this is back in 2014, but I think this stands up to now. And the upshot of it is that basically, even though the science and exploration communities want different things out of the measurements that we need are, for the most part, the same. And those are shown in the middle part of this Venn diagram here. So there's very few measurements that only the science community cares about. And likewise, few measurements that only the exploration community cares about. And so these measurements that Lunar Flashlight will make are important both for the science and for exploration and ISRU. Next slide, please. The motivation for wanting to make yet more measurements is that our existing data sets are often confusing or even in conflict. And so this is just one example of a region in the moon's south polar region with 3 craters, Hayworth, Shoemaker, and Faustini, that show differing amounts of hydration or water in 3 different data sets. And you can argue that they're each probing different depths or different types of water, but the fact is, when you really dig into it, these don't really match up with our models or expectations. And so we need to address this problem. And I think the main reason for this is mostly a signal to noise issue. And so we just need better and more measurements of, in this case, the water frost distribution that Lunar Flashlight will measure. So next slide, please. So the Lunar Flashlight mission has a very short duration. Again, it's a very high risk, high reward kind of operation. So it's a 6U CubeSat that will be launched on the EM1 launch of SLS. It's the first flight of SLS.
2 minutes left, Paul.
Thanks. So we use the measurement approach, and again, the objective is to detect water ice on the surface of the PSRs. We use lasers in 4 different bands to differentially to measure the differential reflectance at those different wavelengths. So it's a long period orbit, a near rectilinear halo orbit with a very long period that gives us about 10 science passes during the 2-month primary mission. Next slide, please. This kind of details the measurement approach and the spectral bands that we're going after. So if you look in the middle bottom panel, our A, B, C, D bands are the different wavelengths of the lasers, and we've picked those to target these absorptions of water frost that we expect on the surface. And we fire the lasers in sequence, A, B, C, D, like that, over and over again. And within each integration of about 1 kilometer long, we get many of those laser pulses. And so we integrate those as reviewed by the optical receiver. Next slide. I'm going to skip this. This is the ConOps. So just as an example, and I see that the animation is not playing, but we did some work led by Jose Martinez Camacho, who's now at SMU, looking at the radiometric modeling and the kind of data that we expect to get. So if you could see the animation, you would see this little laser dot advancing across the orbit track, and we can get good signal to noise within about 25 kilometers of the surface. Our
5 minutes.
Our periaps is at 15 kilometers altitude. Next slide. The summary is that most of the hardware is complete. The system level integration is going to begin this fall. We also have the GDS in development at UCLA and JPL. Ground calibration is ongoing. We've been doing some radiometric modeling and science simulations at CU Boulder, and the delivery of the spacecraft is planned for next spring. So these will be direct measurements of surface water frost from a CubeSat at multiple locations within the PSRs.
Thank you, Paul, for that great talk.